Today, I'm going to talk about from DevOps to MLOps, a journey of scaling machine learning models to 2 million API requests per day. So, before we dive in, a brief about me. I am Chinmay. You can find me on Twitter, LinkedIn, etc. via Chinmay185. I am a founder at a company called 1 to N, where we help startup and enterprises with backend and site reliability engineering. I write stories of our work in called what is called pragmatic software engineering. These stories I publish them on Twitter, LinkedIn, etc. I love engineering, psychology, percussion, and I am a huge fan of a game called Age of Empires. All right, so let's start. So what are we covering today? We are covering three things fundamentally. One is what is MLOps? How do you think MLOps for DevOps practitioners? Fundamentally, I want to talk more about and spend more time in talking about a real world production case study that we worked on, which will talk about all the learnings that we had into in a case study kind of walkthrough. So, what is MLOps? Fundamentally, MLOps is operationalizing data science. We all know what DevOps is. DevOps is operationalizing software delivery, right? Software engineering. Similarly, MLOps is equivalent to DevOps in a sense it talks about operationalizing data science workloads. Think of machine learning, AI, ML workloads essentially, right? So that means it is all about moving machine learning workloads to production. Just like we have DevOps phases, we have various phases in MLOps. Fundamentally, it's like build, where you build the models, you manage various versions of the models, for example, you deploy these models on production, you monitor, you take feedback, you continuously improve the models, etc. So these are various four steps of MLOps. Let's look at some of them in more detail, right? So fundamentally, just like software engineering is about building and shipping code to production, MLOps is about building machine learning models. Now, what do you need for building machine learning models? You need data. Data, you need to extract this data in various forms. You will need to analyze it. You will need to sort of prune some parts of data. Essentially, you're doing data preparation and gathering. Then you feed in this data to your ML model. You will train the model. You will evaluate model's response. You will test and validate whether the model works correctly or not. You will fine tune this process over time. You'll have test data segregation, you'll have production data, stuff like that. This is all the machine learning part of it, which is what data scientists work on. Now, the operational parts of it are model serving. How do you serve this model to production? How do you run this on GPUs? Do you run this on CPUs? Which cloud provider do you want to use? How do you monitor the model, whether it's performing as per expectations or not? How do you manage scale up and scale down of that model? All of that is the operational concern, which is the ops part of it. Fundamentally, this is around a feedback loop. Just like in software, we have CI/CD, continuous integration, and continuous delivery deployment. We have a third parameter or third item in MLOps called continuous testing and training, right? Where you're going to continuously monitor and train the model and improve the model over the period of time. So here is what simplest MLOps workflow looks like. This diagram is from sort of Google's MLOps guide. You can find the link in the description. Fundamentally, again, it starts with getting data, right? So we are trying to map all these previous steps and phases that we looked at into this model. So we're going to get some data from various sources. It could be offline data, it could be real-time data, things like that. For now, we're keeping the diagram very simple and just looking at some offline data. For example, we're going to extract this data, analyze it, prepare that data essentially. And that's the second step. Then the whole model training step appears where you are going to train the model, you're going to evaluate the model, you're going to check the performance, you're going to manage various versions, validations, etc. Finally, you have a trained model which you put into model registry. Now, once that model registry has the model, the operational part of the MLOps comes into picture, which is serving the model, and then which is where you have, for example, a prediction service, right? Which you can run on production. Then you have to monitor, scale that service, run this on GPUs, figure out cloud cost optimizations, etc. around all of that, right? So that's operationalizing data science. That's the simplest MLOps flow that you can think of. You can also map this into a classic DevOps infinity loop, right? So the typical DevOps infinity loop talks about, your code, build, test, plan, then release, deploy, operate, monitor, and doing this in a loop consistently over long periods of time, right? So similarly for MLOps, it kind of starts with having data preparation. You're going to prepare the data, you're going to train the model. Again, that's a build and a test part of it. Then the release will go into model registry. You're going to then monitor the model performance. You're going to deploy the model, monitor the performance, and all of this all together would be continuous training and testing of the model, right? Enough about theory. What I want to talk more about is a use case that we worked on. So this is a production work that we worked on. I'm going to cover the use case at a high level. I'm going to talk about what work we did, how we applied the DevOps and MLOps practices, best practices in production, and the kind of issues that we faced during the production journey, right? So let's start with the case study that we had in mind. So we were working on we were working with a company which was building ekyc SaaS APIs, which was accessible to B2B and B2C customers. This needed to scale up to 2 million API requests per day to the model. Now, the SaaS APIs, these 3 or 4 APIs that we had, one was face matching API. Imagine you provide 2 images to the model. You're going to have to match the face between 2 images, and model outputs a score between, say, 0 and 1. Based on the matching score, you can decide if the 2 images, if the 2 people in this images are same or not. And that's a face matching API. Then we have face liveness detection, which is if you have an image of a face, is this face of a live person or is this a face of a non-alive person? Then we had an OCR or optical character recognition from an image. For example, you upload a photo of a passport or any identity card, you would be able to extract the text information from it, right? So that, imagine this KYC use case for any insurance or a telecom or any other domain, people would have to manually enter a lot of information for the user, like their name, their date of birth, their address, etc. All of this information gets captured via the OCR API, and you get that information returned via response in a structured fashion. So that eliminates having to type and mistype information, right? So similarly, we had some other small APIs as well, which I'll ignore for now. So fundamentally, we had this ML system, and the architecture of that system, along with other components, was something like this. So it was served for mainly for B2B use cases. We also had some things for B2C, but again, we'll ignore that for now. So imagine from a B2B use case, I'm an insurance or a telecom company. I have my own app, and there is a client SDK in that app that I need to install and run, right? I need to package the client SDK as part of my app. Now, this SDK talks to our backend APIs, which are these ML APIs exposed via an HTTP API, for example. So it connects to, for example, load balancer. We have an API layer. Then to be able to serve these models, we had a RabbitMQ as another, like a queue mechanism, where we would push messages. For example, we want to match 2 images, right? Face recognition or face matching across 2 images. We would create a message in RabbitMQ, push that message on RabbitMQ, and there is these background workers, which are these ML workers, which would accept message from the RabbitMQ. They would do the processing. They would update the results in database. Maybe they would even save the results in a cache like Redis, which we had. And the images themselves can be stored in a distributed file store, could be Minayo, could be S3, things like that, right? So essentially, these workers would perform the bulk of the task, and then the API would return the results to the user, right? So this is the kind of architecture we had. Now, what were the requirements from a SLO point of view, right? So we set out for achieving at least like 2 nines of availability, that is 2 nines of uptime, during peak hours or during our business hours. Because we were dealing with a B2B company, there typically would be business hours. Typically, stores would open at 9 a.m. in the morning and would go on till like 10 p.m. in the night, for example, right? The local time. So we had promised like 2 nines of uptime during that in terms of SLO. We obviously had to worry about costs and optimizing the cost as a important requirement from a SLO point of view. We hadn't defined specific metrics, but we'll get to that later. And then from an API point of view, these were synchronous APIs as far as the user and the SDK is concerned. So less than 3-second API latency for 95th percentile. That was our goal that we had set out. Now, given this, let's think about our architecture, and we set out to build a cloud agnostic architecture. I'll cover more of that soon and why that is. So, for example, for the storing of actual images, which were ephemeral for short time and whatnot, because again, we're dealing with sensitive data, we were using S3 if we are deployed on AWS, we were using GCS if we were deployed on GCP, and MinIO if we were deployed on-premise. One of the reason was that we wanted to have same code could use different type of image store without having to change the code a lot or without no change to the code at all. Why? Because then we could deploy this entire stack on any cloud. We could run it on-premise. We could even run it on customer's premise. We could run it on AWS, GCP, or any other cloud for that matter. This was the main point that we wanted to achieve. That's why we set out to have a cloud agnostic architecture where we don't use a very cloud specific component and then we are tied to that particular cloud as a code dependency, right? Now, that's for MinIO. For Redis, we could either go with self-hosted Redis, which is basically a cache for storing bunch of latest computation that API can quickly return the results to the users. We could do this as a self-hosted Redis or Elastic Cache if we are on one of the cloud providers. Now, for RabbitMQ, we again chose RabbitMQ purely so that we could run this on-premise easily. And if we were on a cloud, we could use something like SQS or like equivalent, right, in either cloud. For GPUs and workers, which were predominantly GPU workload, we would use them on one of the cloud providers, or we could get our own custom GPUs, etc. For this production use case, we were on one of the cloud providers, and so we use most of the cloud components, but our code was such that it was not tightly coupled to cloud at all. And for database, again, we could use Postgres, it could be RDS or Cloud SQL or something else, depending on the cloud provider. So, and we fundamentally had Nomad as the orchestrator, which would orchestrate all the deployments and scaling of components. Back then, we were not using Kubernetes purely again from a simplicity point of view that we wanted to deploy this whole stack with the orchestrator on premise. And we didn't want to, in the team, we did not have a lot of Kubernetes expertise to be able to manage self-hosted Kubernetes on-premise ourselves. So that's where we chose HashiCorp stack, which is fairly single binary, easy to manage and easy to run. And we already had expertise in the team for that. Why cloud agnostic? I think this is a very important point that I want to highlight. Because we were cloud agnostic, we could package the same wine in a different bottle, for example, right? So we could package the same stack and run it on any environment that we wanted to. We could do air-gap environments if we had to, things like that, right? So this was the main reason why we went cloud agnostic. And I think one of the lessons to learn is to build more cloud agnostic systems. That way you're not tied to any of the cloud providers. Although using cloud providers obviously simplifies a lot of things for you, but you would want to have your architecture and code not coupled with the cloud provider, right? So that you can change freely and migrate to a different cloud if you want to, without having to redo a lot of effort. What did our scaling journey and how did we go from 0 requests to 2 million API requests per day? Right? Let's talk about that. Obviously, it wasn't 0 requests one day and 2 million the next day. It was a gradual scaling journey, something like this. So we would roll out on few regions or few stores, and then we would slowly increment the traffic. We would observe the traffic and so on and so forth. So fundamentally, from our scaling journey, I want to talk about 4 or 5 important points and then drill down on each one of them as we go through the talk. One is the elimination of single points of failure. Right? To be able to scale, we want to have 0 or no single point of failure so that your system is more resilient to changes, resilient to failures. We also need to do good capacity planning so that you're able to scale up and down very easily and you can save on cloud costs. Otherwise, if it requires you to scale and you are having to do a changes to the architecture, it causes problems, right? So having good capacity planning and how we went about that, I'll also cover that. Obviously, cost optimization and auto scaling goes hand in hand with capacity planning. So I'll cover that. Then comes around a lot of operational aspects about deployments, observability, being able to debug something, dealing with production issues, stuff like that. And obviously, all of this journey wasn't very straightforward. It was fraught with some challenges that we encountered. So I'm going to cover like two interesting challenges that we encountered along the way. So hopefully you all can learn from it. So in the next part of the talk, I'm going to take each one of these points and then go drill down on each one of them, right? So let's talk about eliminating single points of failure. We had this architecture. I'm just showing the architecture here in the background. So one of the things we did is we added high availability mode for RabbitMQ. What does that mean? It means we have queue replication. So whichever queue is there on one machine, it gets replicated or mirrored onto the other machine. We were running RabbitMQ in a 3-node cluster instead of a single node, for example. Right? We also had cross-AZ deployment for RabbitMQ. So the 3 nodes of RabbitMQ, each one would run its own AZ, for example. Right? Obviously, this was on-premise or a setup where we wanted to host and manage RabbitMQ ourselves. But if it were a cloud-managed service that we would use something like SQS, for example. One of the other things that we did to eliminate single points of failure is to run ML workloads in multiple AZs. Now, back then, we had only 2 AZs where we could have ML GPUs available. The third zone from the cloud provider did not yet provide the GPUs. So we had to tweak our logic and deployment and automation to be able to spin up and load balance between these 2 AZs. So we would have to fix autoscaling, we would have to fix deployment automation to be able to run workloads only on 2 zones instead of 3. For most of the other cloud components or most of the other components in the architecture, we would have workloads run on all 3 AZs. Other thing that we did is wherever possible, we used SaaS offering for some of the important stateful systems like databases, for example, Redis and Postgres. It's just to make sure that we don't have to manage and scale those components also. And managing and scaling ML was one of the bigger challenges. So we wanted to offload some of the lower hanging fruits to the cloud providers. Fundamentally, the idea again is that scaling and managing stateful components is a bit hard and stateless is much more easier. So wherever possible, it's easy to automate stateless application scaling, component scaling, and stateful becomes difficult. So that's on the eliminating single points of failure. Let's talk about capacity planning, right? So always when you think about capacity planning, you think of the bottleneck, right? Because if the strength of the link is the strength of the weakest component in the link, for example, right? Strength of the chain is the strength of the weakest component in the chain. So you want to find out what's the weakest component and improve the strength of that component. Right? So for example, if you think about various components from the architecture, we have API, which is simple API which just talks to database and get the results from database, for example. There is database, which is stateful component. It could be Redis, Rabbit, Postgres, etc. Then ML workers and something else. So where do we think is the bottleneck? Obviously, it was on the ML worker side because that's the component which takes most time in the request path. So we set out to figure out, for example, how many ML model requests can a single node handle, right? So for example, if we have a single node with, say, 1 GPU with 16 gigs of GPU memory and a GPU with whatever few cores, how many workers can I run on that and how many requests per second or per hour can I get out of that, right? Now, each model, ML model, may give us different results. So, for example, face matching may be faster than OCR, or face liveness detection could be faster than face matching, for example. So, we would run load test and we would run each of these models, each of the nodes, and we would run them via a load test to be able to find the maximum throughput that we can get over a long period of time, say an hour or two, for example. Right. So again, I've broken this down into more detail and even more generic format in another talk that I gave, which is optimizing application performance. How do you go about it from first principles? So if you're interested, you can check that out. I'll provide the link in the description, hopefully. Cost optimization, autoscaling. That is one of the pet peeves given the current market scenario. So mostly you will have seen if you use GPU in cloud, it costs a lot, right? So how do you go about optimizing and autoscaling? So you have to think about what is the parameter on which you can autoscale. Like, is it the utilization of CPU or GPU? Could it be based on memory utilization or number of incoming requests, for example, right? Or it could be depth of the queue in case we were using RabbitMQ. So could it be queue depth or something else? Now, we kind of used a combination of some of these components. So I'll talk about how we went about. So this is the cost optimization autoscaling, like our autoscaler, how it works, right? So on the left, you have top left, you have a current request rate. This is the graph where we would have what's the number of requests we are getting over last 20 or 30-minute interval, right? And we would have a capacity predictor component which would run every 20 minutes, which would fetch this request rate, or it would have this information, and it would also get the current node count or current worker count. So again, imagine we are running these GPUs on workers, right? What's the current number of workers that we have currently? So you would get the current workload, you would get the current request count, and based on that, based on the request number of requests and the growth rate of that, the capacitor, the capacity predictor would kind of predict using just simple linear regression the desired node count. So for example, if we for example open the stores at 9 a.m. and we know that we at least need like 50 machines at that point, so we would have time-based auto-scaling, which would just spin up 50 machines. You have them ready at like before 10 minutes the stores open, right? But the stores open and you continue to see increase in traffic, you would want to spin up more nodes. If you see decrease in traffic, typically during lunchtime, you would want to spin down a couple of nodes, for example, right? So we had this capacity predictor component which would take this request rate, rate of growth or rate of decline. You would take the current node count, and based on the linear regression math and some other parameters that we talked about, it would predict the desired node count. Now, this is the count that would go as an input to autoscaler. The autoscaler would then do a couple of things. It would update Nomad. It would tell Nomad, hey, can you please spin up those many number of components or those many number of workers? So the Nomad update cluster configuration would run, and the Nomad would correspondingly spin up more nodes. It will deploy the model on those nodes, etc. And it would also update, for example, we were using Slack, so it would also update us on Slack that, yeah, we've got 2 more nodes added, or we've got 2 nodes destroyed because it was less traffic time, for example. One of the reasons we built this kind of a system is so that we have a manual override. At any point, if we knew that there is a big campaign going on, or we are going to have to scale the machines at a particular time or due to some other kind of business constraints, we would be able to manually override that value and change the configuration to be able to spin up those many number of nodes. Right? This gave us a lot of control, and we've been using this autoscaler for years now, and it's just been working very well. It's a very simple, less effort work, but it just works flawlessly for us. So we've never had issues with autoscaler as such. There's more that we have written about in our one of the recent like blog posts and case studies. So you should check it out if you're interested in this kind of stuff. Now, our journey wasn't smooth, right? It was fraught with some issues and errors. So I'm going to talk about some of the issues we encountered and how we navigated those and what kind of impact it had on downtime, SLO, etc. So one of the issue that we encountered was GPU utilization in Nomad. For example, imagine this top box to be a GPU. It has GPU cache, memory, and cores. We would be able to run a ML worker using Nomad using Docker driver. So we would run one ML worker per GPU. What we noticed is that the GPU wasn't utilized fully. It was with one worker, it was just 20% utilized. And a lot of other resources of that machine were just left unused. We did load test to be able to figure out how much throughput we can get out of a single machine running single ML worker. It's a Docker container, and it wasn't impressive. With this, if we just ran with this kind of hardware, our cost was going through the roof, and we had to really figure out how do we fix this. So we dug deep into Nomad, GitHub issues, some pull requests, some parts into reading obscure documentation and figuring out. And fundamentally, later what we discovered is one workaround which we can use, which is instead of using Docker driver, if we use raw exec driver, which allows you to run any kind of component, it doesn't then guarantee any like you have to worry about a lot of scheduling yourself when you use raw exec driver. But with raw exec driver, you could run Docker Compose, and we spin up multiple Docker containers using Docker Compose via raw exec driver in Nomad. So what that allowed us to do is the same GPU machine, we could run not one, but 4 workers, right, using Docker Compose. Now that led us to having about 80% utilization. It straight away brought our cost down by 4x. So imagine if we had to have $100,000 per month on just on GPU, we would slash it by 1/4 directly and have like 400% impact essentially. So this was one way we solved it. This is, as of today, last I checked, it is still open, this issue, and you would see this pull request or this issue is still open. And one of the solutions or workarounds that we've used, I've highlighted that here for you to look at. One thing that we noticed, if you use raw exec driver, you're going to have to worry about the shutdown part of it yourself. So otherwise, Nomad generally handles sick term, and it handles the graceful termination of resources or components. In this case, you will have to have waits and timeouts, and you have to do some magic and work. You have to put in some work to be able to tear down the components correctly. So we invested in that, and we wrote some bash script to be able to run, which could run the components and also tear them down easily when we wanted to. One other issue that we encountered is high latency. So again, like we have steady traffic, new regions or new stores are opening up, and we are getting them migrated to use our APIs, and the rollout is happening. Suddenly, on one of the days, what we see is that more than 25-second response time. Now imagine like our SLA is less than 3 seconds response time for 90th percentile or 95th percentile. Now we suddenly get 25 seconds of response time. That's unacceptable. So we debug this issue. We try to find out, there must be some problem with ML worker, right? Because that's the slowest component in the chain. But we realize that there is no queue depth. The workers are doing their job. There is no extra jobs for them to be processed. So the worker scaling or auto scaling is not a problem. But then why do we have this much latency on the API side? There is no processing lag on the worker. Why do we have that? We spent a lot of time debugging this issue, and ultimately we discovered that the number of Go routines that we had on the API side, which would process the results from RabbitMQ. So for example, our flow was that we would have the client SDK call our NLB or ALB. The API would send a message to RabbitMQ. The workers would then consume that message, produce the result. It would be updated on database, and it would also send another message on to RabbitMQ that the processing is done and some other metadata. Now there is this workers that were running on the API, which would then consume this metadata via the RabbitMQ message, and then it would return the response to the user or do something else, right? Now that's the part. We were just running 5 Go routines. Now what we realized is that we were also running 3 nodes or 3 Docker containers for workers, and we never faced any issue with worker. The CPU utilization API layer, we never faced any CPU utilization or any issue with API layer. But when the request count increased, what we realized is that these 5 Go routines were not enough, and which is where we're actually seeing queue depth on the API side. The API Go routines that were trying to consume from RabbitMQ, that's where we saw the queue depth. And it took us a while to figure this out and to fix this, because our preconceived notion and the first response was to look at workers as a problem, right? Now we changed the Go routines to 30, and suddenly the flip the traffic goes normal and we have less than 3 seconds response time. So that really shows how you want to how you should understand the components and how data pipeline works, and you need to really think about where the latency is being introduced. After that, we also added a lot of other observability signals and metrics to be able to track this issue and further any other issues even further. So we invested a lot in tracking cross service latencies and stuff like that. So I've written about this as a form of pragmatic engineering story. You can check it out on Twitter if you follow me there. I want to conclude this session by talking about some of the lessons that we learned along the way, right? So one is, for ML workloads, it goes without saying, but it's worth repeating, that data quality and training the model is super important. Like, a lot of it depends on the quality of data and the volume of the data, and how you train your models, how you carve out the test data versus the data that you run the model on and you want to check, and you how you label and annotate the data, right? So a lot of it depends on data quality and training. In our case, and I would highly recommend to use cloud agnostic architecture to be able to build scalable systems that can give you that flexibility to deploy them on any type of workload or any type of underlying cloud, right? For us, that has been the massive win, and I would highly encourage you to think about building cloud agnostic systems. One of the things that I've seen majorly is people do not treat operational workloads as first class citizens. They just slap on top of the existing software and just say that, yeah, somebody will manage this. But treating operational work as first class citizen really helps in automation of a lot of your day-to-day tasks, and it gives you, especially when you are first launching, you should really treat production, maintenance and operations as a first class citizen in software building and delivery process. Lastly, from a team point of view, we had really good collaboration with various teams, right? Data scientists, the mobile SDK team, the backend engineering team, SREs, and even the business folks. So, for example, whenever there is a new campaign, or we would get some info from business team that a new region or new bunch of stores are being onboarded, preemptively scaled the nodes to be able to handle that traffic, for example, right? So being able to closely collaborate with data scientists, we also optimize, for example, one of the case, we also optimize the Docker image size for the models. Earlier, we would have all the versions of the models in our final Docker image, which would mean the Docker image itself would be like tens of GB. So we'll have 10 GB Docker image. Later, we optimize that with close collaboration with the data scientists to less than like 3 GBs of model, right? So that just speeds up a lot of warming up of nodes. It just speeds up the deployment process and the time it takes for nodes to be ready to serve traffic. So ensuring good collaboration between teams is super, super important. I think that's it from my side. What I would say is connect with me on LinkedIn, Twitter, etc. You should check out our Go or SRE bootcamp that we have built at 1-2N, along with the software engineering stories that I write. Here's the QR code. You can scan this and you can check this out.